So picture this. Just close your eyes and imagine it's 66 million years ago.
Right at the end of the Cretaceous.
Exactly. The dinosaur apocalypse has just hit the absolute reset button on the entire planet. Like an asteroid strikes, the sky goes completely black with ash, and global forests just collapse.
Total ecological devastation.
Yeah, and all the heavyweights of the planet, the T-Rex, the Triceratops, they are just wiped off the board almost overnight.
It's a catastrophic collapse. I mean, the absolute peak of the food chain is just erased.
And that leaves this sudden, massive power vacuum. But as the ash finally starts to settle and the world begins to drastically warm up, something new basically slithers out of the shadows to claim that top spot.
And it's not something you would ever want to run into.
No, definitely not. Looking at the sources for today's deep dive, especially this incredible investigation by Apex Truth, we're going to piece together this terrifying picture of what took the throne. We are diving deep into Titanoboa.
Just the name alone carries a certain heavy gravity, doesn't it?
Oh, it completely earns it. I mean, imagine a snake that is longer than a standard city bus.
A literal monster.
Yeah, a predator that weighs as much as a small car. And we're talking about a constricting force that mathematically is equal to being crushed inside the jaws of an industrial car compactor.
Which is just an unfathomable amount of pressure.
Right. This was a creature that could wrap around a giant prehistoric turtle, snap a half-meter thick shell like a cracker, and just casually swallow a 2-meter-long crocodile whole.
It really is the stuff of absolute primal nightmares. But, our mission for this deep dive isn't just to gawk at a scary movie monster.
Right. We want the actual science.
Exactly. We're unpacking this unbelievable scientific detective story that completely upends our understanding of evolution and gives us a really stark window into Earth's climate history.
Okay, well, let's unpack this then. Because to actually find this monster, we have to start in what feels like the most unlikely hostile place on the planet. We're fast-forwarding to modern-day Colombia.
To the Cerrejón mine.
Yeah, the Cerrejón open-pit coal mine. And just to paint a picture for you listening, this place is a forbidding, dusty, sun-baked wasteland. It covers 700 square kilometers.
Which is massive.
It's a crater larger than the entire city of Chicago. It's just this endless barren horizon of brown dirt and massive industrial dump trucks and extreme heat, and they extract like 19 million tons of coal every single year.
And that right there is the supreme irony of this entire investigation.
How so?
We sit in that exact same spot 60 million years ago in the Paleocene epoch, which is literally right after the dinosaurs went extinct. You wouldn't be in a dusty wasteland.
Right.
You would be drowning in a sweltering, hyper-dense tropical swamp, like significantly hotter and wetter than the modern Amazon rainforest.
Oh, wow.
And the wild part is all of that lush, ancient organic matter from that jungle, the massive trees, the giant ferns, so all that decaying biomass, that is the coal they are mining today.
So millions of years of heat and pressure basically turned that jungle into the rock they're blowing up right now.
Precisely. The mining process is actively destroying the ancient landscape, but it's simultaneously serving as our only functional window into this complete ancient ecosystem.
Which perfectly sets up this bizarre mystery from the 1990s. So there's this geologist out surveying the Cerrejón mine, and he finds this chunky, unfamiliar fossil.
Just sitting out there.
Yeah, and he isn't a bone guy, right? So he just slaps a label on it that says petrified branch, and he puts it in a glass display case right in the coal company's corporate reception lobby.
And there it sits.
Gathering dust. For 9 whole years.
I mean, hundreds of people, engineers, executives, visitors, just walking right past it, getting their morning coffee, completely unaware.
It's like using a winning lottery ticket as a paperweight for a decade, just totally oblivious to what you're resting your mug on.
The scientific value is astronomical, but it required the right set of eyes.
And those eyes finally show up by pure accident. A geology student is wandering the edges of the mine and accidentally discovers these perfectly preserved fossilized leaves.
Which is a huge deal for paleobotanists.
Right, so it brings Scott Wing, a guy from the Smithsonian, down to the site. Wing is there exclusively for the leaves, but when he walks into that corporate lobby to sign in, he completely ignores the receptionist and spots that dusty, petrified branch in the glass case.
Because his professional instincts just override everything else. He knows wood grain, and he knows that isn't wood.
Exactly. He immediately snaps pictures of this thing through the glass and emails them to a paleontologist named Jonathan Block. And here's the crazy twist. It wasn't a piece of wood at all.
Not even close.
It was the massive fossilized jawbone of an extinct marine crocodile. a creature called a dinosaur.
Which completely changed the game.
But wait, I have to stop you there because that makes no sense. If this was a marine crocodile, a saltwater animal, what on earth was it doing buried deep inside an inland coal mine in Colombia?
See, that is the exact right thread to pull. Finding a marine giant buried inland proved that this site wasn't just some random forest. It was once a massive coastal swamp ecosystem connected to the ocean. And more importantly, if you have apex predators like giant marine crocodiles living in this swamp, it strongly hints at the carrying capacity of that environment.
Meaning there had to be a lot of food.
Exactly. A food web that can support giant crocodiles means there is an unbelievable amount of biomass thriving there. And huge prey means the potential for even larger predators.
So finding out these predators were hiding in the coal kicks off an absolute gold rush. In 2004, a team mounts an expedition to an active section of the mine called the La Puente Cut.
And the day-to-day reality of this dig.
Oh man, apocalyptic doesn't even begin to cover the conditions.
Yeah, it was certainly not your standard leisurely fossil dig with tiny brushes and sun hats.
Not even close. I mean, they are working at the bottom of a massive coal pit near the equator. The ambient temperature is consistently over 30 degrees Celsius.
With zero shade.
Just baking in the sun on black rock. Spontaneous methane fires are constantly erupting around them from the coal seams. They have 40-kilometer-per-hour winds blasting their faces with toxic coal dust.
It sounds like an absolute nightmare.
And if that wasn't enough, they get hit with daily torrential tropical rains that completely wash away all the painstaking digging they did the day before.
The physical toll on the team must have been immense.
It really was. But their suffering paid dividends because what they started pulling out of that gray mud was just staggering. They found turtle shells that were 1.5 meters wide.
Think about a snapping turtle the size of an 8-person dining room table.
So we aren't just talking about a giant snake later on. We're talking about an entire ecosystem on absolute steroids.
Entirely. They found 3 totally new species of ancient crocodiles.
Oh.
One of them actually had a jaw structure specifically evolved for a literal death bite.
A death bite?
Yeah, its snout was heavily reinforced, built mechanically to pierce those dining table turtle shells that were 0.5 meter thick. It was a brutal, hyper-competitive land of giants.
And yet they still hadn't found the true king of the swamp. So let's fast forward to 2007. The team has been shipping hundreds of these plaster-wrapped fossil casts back to a lab in Florida.
Just massive crates of material.
Right. And a grad student is doing the deeply unglamorous grunt work of unwrapping these packages. He opens one up and pulls out this giant, strange-looking vertebra, a backbone.
And because of its sheer size, the field team had originally labeled it as a crocodile bone.
But he looks closely at the shape, calls his lab partner over, and the lab partner drops this absolute bombshell. He looks at it and says, "That's a snake."
We really have to pause here to grasp the sheer scale of the bones sitting on that lab table.
It's hard to even wrap your head around.
Right, so to give themselves a baseline, they went to their fossil collection and pulled out the vertebra of a modern-day anaconda, one of the largest, heaviest snakes alive today.
Okay.
The ancient vertebra from the Sarahon line was 3 times larger than the anacondas.
3 times the size of an anaconda backbone. That's terrifying.
It was so massive that leading paleontologists, people who have spent their entire adult lives analyzing reptilian anatomy, had actually been tossing these exact same snake vertebrae into the rejection pile for years.
Wait, really? They were just throwing them away?
Yeah. Their brains literally couldn't process the size, so they assumed they were crocodile bones. Jonathan Block famously likened the experience to someone handing him a mouse skull that was the size of a rhinoceros and trying to convince him, no, really, this is just a mouse. You instinctively reject it.
Okay, but here's where it gets really interesting. Because having a few massive backbones is a great clue, but snake skeletons are notoriously fragile. They almost never survive intact.
They're mostly ribs and very delicate connections.
Right, so you can't just lay out a full skeleton on the floor with a tape measure to see how long it was.
Right, they had pieces of a puzzle, but no box to show them the final picture. They had to rely on complex mathematics.
Hold on, I need to challenge this though. How can you accurately calculate the total length and weight of an entire snake from just a handful of backbones?
It's a fair question.
Don't snake spines taper? Like the bones near the head are smaller, the ones in the middle are huge, and they get tiny again near the tail. How do they know they didn't just find the single biggest bone of a slightly above average snake?
That is exactly why they had to bring in a specialist, David Pauly, who built a highly specific mathematical model. You're completely right, the spine tapers.
So how did he figure it out?
Well, vertebrae aren't just uniform blocks. They have incredibly complex geometry. Polly looked at the subtle angles of the neural spine, the part that sticks up, and the zygapophyses.
A what?
Zygapophyses. They are the little interlocking joints that connect one vertebra to the next. By plotting the exact coordinates of every ridge and slope on that giant bone onto a digital graph, he could identify exactly where in the spinal column that specific bone belonged.
Oh, wow. So it's like finding a puzzle piece and knowing exactly what row and column it fits into.
Exactly. And once he knew its position, he mathematically scaled those dimensions against the skeletal structures of modern boas and anacondas to extrapolate the rest of the body.
And the result of that math, which they formally revealed to the world in 2009, was the naming of Titanoboa cerrigonensis, 13 to 15 meters long, weighing 11,135 kilograms.
A literal ton of snake.
Just to anchor that in reality for you listening, the absolute largest modern anaconda ever reliably measured by scientists was only about 8.5 meters. Titanoboa was practically double that length and exponentially heavier.
It was a true biological behemoth.
Yeah.
But knowing its sheer mass only answered the what. It didn't answer the how.
Right, like how did a snake the size of a school bus actually function?
How did it move without crushing its own organs?
Yeah.
What did it hunt in that swamp?
Because you clearly can't have a 1-ton snake silently slithering up a thin tree branch to ambush a bird.
Exactly. And to figure out the day-to-day hunting strategy of this monster, the team needed the ultimate holy grail of paleontology. They needed a skull.
Which is basically asking for a miracle. We need to explain why finding a snake skull is like finding a needle in a haystack if the needle was made of dust.
It's nearly impossible.
Right, because snake skulls aren't made of thick, fused, solid bone like a human skull or a T-Rex skull. They are these incredibly delicate, fragile frameworks of dozens of tiny bones held together almost entirely by soft tissue, tendons, and ligaments.
So when a snake dies, and that soft tissue rots away in a wet swamp, the skull doesn't stay in one piece.
It just shatters.
Yeah, the tiny bones disconnect and scatter into the mud, often washing away completely.
Yeah.
So hoping to find an intact snake skull inside an active industrial coal mine where Earth is being moved by the metric ton, it was a complete pipe dream.
But then, in 2011, against absolutely all odds, the mine delivered. They didn't find a pristine, fully intact skull, but they found 3 individual, unmistakable skull bones.
And what's fascinating here is how much mechanical data you can extract from just 3 specific fragments if you understand the architecture of a snake's head.
So walk us through the mechanics. What did those fragments actually prove?
Well, the most critical piece they recovered was a special hinge bone called a quadrate. And in Titanoboa, this bone was elongated and allowed the lower jaw to pivot and extend far behind its brain case.
Like a giant military cargo plane. When the back door unhinges and drops all the way down to the tarmac to load a tank, that's what Titanoboa's jaw was doing.
That is a perfect visualization. It meant the snake could open its mouth impossibly wide, much wider than even its massive 1-ton body size would suggest.
That's terrifying.
And then there was the jaw fragment holding the teeth. The socket spacing showed that its teeth were very closely packed together. In the modern snake world, that specific tight dental trait belongs almost exclusively to snakes that specialize in eating fish.
Oh, wow. So that completely changes the picture. It wasn't just roaming the dry jungle floor, snapping up land mammals.
Precisely. Titanoboa was a semi-aquatic ambush predator. Think less like a boa constrictor in a tree and more like a supersized water anaconda.
That makes so much sense.
Yeah, dragging over 1,000 kilograms of muscle across dry land would burn an unsustainable amount of energy. But in the water, the buoyancy of the water literally displaces that mass, supporting its massive weight effortlessly.
So it would just lie almost perfectly still, camouflaged beneath the surface of those dark, tannin-stained swamp waters, which just means the water was a murky tea color from all the decaying leaves. It would just wait in the dark for a giant fish or a 2-meter crocodile to swim just a little too close.
The ultimate lurking nightmare.
We now know what it was, how big it was, and exactly how it hunted. But that leads us to the biggest question of this entire deep dive. Why did it get so astronomically huge in the first place?
And the answer to that doesn't actually lie in the water. It lies up in the atmosphere.
Right.
It comes down to a fundamental rule of reptilian biology. Snakes are ectotherms.
Also known as cold-blooded.
Right. But it doesn't mean their blood is actually cold. It means they don't generate their own internal body heat like mammals do. They rely entirely on the external ambient heat of their environment to run their cellular metabolism.
So they need the sun and warm air to function.
Exactly. The warmer the air and water around them, the faster their metabolism runs. A faster metabolism means they can process more energy, digest larger prey, and crucially, physically grow to much larger sizes.
So for a snake to reach 1,135 kilograms, the climate of the Paleocene tropics couldn't just be a nice warm summer day. It had to be a relentless, sweaty, global sauna.
Exactly.
Yeah.
The fossils themselves act as a prehistoric thermometer. By calculating the minimum ambient heat required to sustain the cellular biology of an ectotherm of that massive size, scientists proved that the ancient average temperatures in that region were between 30 and 34 degrees Celsius.
Wow.
And that isn't the daytime high, mind you. That is the average year-round temperature, day and night. It was staggeringly hot.
So what does this all mean? Because this creates a really intense paradox for you listening right now. Today we know that rising greenhouse gases and extreme heat cause devastating consequences.
Absolutely.
We see coral bleaching, massive plant die-offs, and animal extinctions happening right now. Yet when paleobotanists studied those fossilized leaves found at Sarahan, they discovered that carbon dioxide levels back then were 50% higher than they are today.
It's a huge difference.
If CO2 is destroying our ecosystems right now, how did 50% more CO2 back then create a thriving, lush, tropical paradise full of giant animals? That feels entirely contradictory.
Well, if we connect this to the bigger picture, it all comes down to one critical underlying mechanism: the variable of time.
Unpack the timeline for us.
It is the time scale difference that dictates survival versus extinction. The ancient warming period that created that Paleocene sauna didn't happen overnight. It happened gradually, creeping up over millions and millions of years.
It was incredibly slow.
That geological pace gave entire ecosystems, the plants, the insects, the reptiles, the time they needed to genetically adapt. Generation by generation, they evolved and shifted in tandem with the climate, eventually achieving this incredible gigantism.
They matched the pace of the changing world.
Precisely. But today, the anthropogenic climate change we are experiencing is happening over mere centuries or even decades. It is a violent shock to the biological system.
It's happening far too fast for nature to biologically adjust.
Right? The genetic tools for survival are absolutely there. As Titanoboa proves, life can thrive in high heat and high CO2 environments. But the mechanism of evolution requires immense amounts of time to deploy those tools.
So when change happens this fast, ecosystems collapse before they can adapt.
That is a staggering perspective.
Yeah.
It's not that the heat itself fundamentally destroys life, it's the speed of the heat that makes it lethal today.
Which brings us to a wildly popular internet rumor we absolutely have to address, because if you spend enough time scrolling, you've probably seen the viral videos or forum posts claiming that just like the megalodon shark theories, there's a bus-sized snake still hiding in the unexplored deepest depths of the Amazon rainforest today.
People love a good cryptid story.
They really do. Could Titanoboa still be out there right now?
I have to shut that down completely. I know. But it is biologically and ecologically impossible for Titanoboa to exist today for a few very concrete reasons. First, looking back at the ectotherm biology we just discussed, the hyperwarm climate required to sustain a 1-ton snake simply doesn't exist anywhere on Earth right now.
Not even in the Amazon.
Not even in the most remote, sweltering parts of the Amazon basin. It's too cold.
So mechanically speaking, if you dropped a Titanoboa into the modern Amazon, its metabolism would just stall out. It would become sluggish and eventually freeze to death, biologically speaking.
Right. It physically could not process enough energy to live. Furthermore, an apex predator of that colossal size would entirely alter the modern food chain.
It would need a lot of food.
Massive amounts of huge prey. You can't hide a predator that eats 2-meter crocodiles for breakfast. It would leave massive ecological footprints, depleted populations of large animals, physical disruption of waterways, stuff that we would undeniably see. A 1-ton predator doesn't get to live off the grid.
So you can sleep easy knowing there are no giant snakes waiting for us in the Amazon. But what an awe-inspiring journey this investigation has been.
It really highlights the resilience of life.
We started with a forgotten, dusty, petrified branch holding down papers in a corporate mining lobby, and it ended up being a discovery that totally redefined the absolute extremes of nature. It showed us exactly what the biology of this Earth is capable of producing when the temperature dial is turned all the way up.
This raises an important question, though, as we wrap up.
Oh.
While Titanoboa is safely confined to the fossil record, the Earth absolutely holds more secrets buried in the dirt.
I like where this is going. What else is out there?
Well, just recently, paleontologists digging in a different coal mine, this time in Gujarat, India, uncovered another set of massive fossilized snake vertebrae. They've dubbed this new ancient species Vasuki indicus.
Wait, really?
Yes, and the largest vertebra they found measured a staggering 11 centimeters in diameter.
Wait, how does that actually compare to the beast we've been talking about?
It firmly rivals Titanoboa's throne.
Mmm.
While we are still waiting on the complete mathematical models, it suggests a creature of terrifyingly similar bus-sized proportions.
Oh, wow.
But this one evolved completely separately on the other side of the planet in a totally different ancient ecosystem.
So next time you're out on a hike and you kick a dusty rock, just take a second to remember what might be right beneath your feet.
Yeah.
What other nightmarish, bus-sized monsters are silently waiting deep under the earth, just waiting for someone to trip over them and dust them off? Thank you for taking this incredible deep dive with us, and we'll catch you on the next one.